Hello, my name is Renelle, and in this presentation I will talk about how to identify and characterize fluid inclusions in atom probe tomography data. Fluid inclusions are void-like bulk defects that are filled with gas or liquid. These features can occur in both natural and engineered materials, and they play a vital role in determining a material's physical properties. In earth sciences, fluid inclusions are commonly used to constrain the temperature and pressure conditions of geologic processes. However, characterizing void-like features in APT brings many challenges due to ion trajectory aberrations. For example, Lloyd et al. 2019 documented voids as high atomic density regions in APT reconstructions, whereas Miller et al. 2011 documented voids as low atomic density regions, and Wang et al. 2020 as a combination of both low and high atomic density regions, with a high density in the center of the feature. In this study, we aim to characterize nanoscale fluid inclusions in natural minerals using atom probe tomography. To do so, we've conducted APT on a natural fluid inclusion-rich iron sulfide aggregate, which is imaged here on the right, and we have compared our data to numerically simulated experiments. For the simulations, we used a model that emulates the thermally activated process of field evaporation, which was developed by the Groupe de Physique des Matériaux at Normandie Université. This model was chosen for its ability to quantify and correct APT biases related to local magnification effects. Now on to some results. Here we show a reconstruction of the sulfide sample, showing a homogeneous distribution of iron in the pink or purple dots, and clustering of arsenic shown with the turquoise isosurfaces, and oxygen shown in the red isosurfaces. These element clusters correspond to high atomic density features shown with a gray isosurface in figure C, and are defined by arsenic-rich spheres overlain with oxygen-rich disks in the direction of evaporation. To confirm that these high atomic density features are fluid inclusions, we ran field evaporation simulations of simplified core shell particles in a pure matrix. The shell represents the arsenic-coated margin of a fluid inclusion, whereas the core represents the oxygen-rich fluid inside the inclusion. The matrix here is assumed as a simple cubic crystal structure with a lattice parameter of 0.2 nanometers. For the simulation, the evaporation field of the core is set to 0.1 times that of the matrix, and the evaporation field of the shell is set at 1.1 times that of the matrix. For simulations 1 to 3 here shown on the left, the initial core shell particle has a size ratio of 20.6% relative to the specimen tip radius, with shell compositions varying from 10 to 100 atomic percent arsenic. And for simulations 4 to 6 shown on the right, the initial core shell particle has a ratio of 9.1% relative to that of the tip radius, and shell compositions also varying from 10 to 100 atomic percent arsenic. Regardless of the parameters, all 6 simulations reveal similar results. The pre-evaporation spherical shells mostly retain their morphology after evaporation and only appear to have a slightly dispersed arrangement of ions. And the initially spherical simulated cores consistently produce dense and irregular ion clusters amalgamated into disc-like geometries at the tip or at the edge of the post-evaporation shells. Here we show composition profiles across the post-evaporation core shell particles, shown here by the lines X to X prime and Y to Y prime on the top left image. In both profiles, we observe a strong positive correlation between the particle's ionic density and its core composition. This correlation is attributed to the crossing of trajectories of the core ions, which result in apparent elevated ionic densities. This correlation is stronger in the larger particles, which can be explained through the masking of the core ion trajectories by the magnification effect of the ions evaporated from the hemispherical specimen surface. To summarize, we show a schematic of the ion flight paths of local composition surrounding a fluid inclusion. In A and B, the ions from the specimen matrix, shown in gray dots, and the fluid inclusion shell, shown in turquoise dots, are evaporating at a similar rate 90 degrees from the hemispherical surface and deflecting towards the specimen main axis, resulting in a homogeneous density of hits on the detector. In C, the fluid inclusion core, shown in the red dots, is exposed and evaporates at a much faster rate due to its significant lower evaporation field, resulting in a very localized high density of hits on the detector. And finally, in D, ions from the fluid inclusion shell evaporate at 90 degrees from its concave surface, resulting in converging flight paths and localized high-density regions on the detector. Thank you for listening.